Okay, having discussed the physical basis of the mind in the brain and the rest of the nervous system, we're now in a position to talk about what it is that the mind does. And it turns out that a major function of the mind is to acquire and use knowledge, to produce adaptive behavior of various kinds. What organisms do, especially human beings, is we acquire knowledge in the form of various kinds of mental representations of the world around us. So we need to form internal representations of the world. That's the job of perception. Store these representations for later use. That's the job of memory. To reflect on and transform and manipulate this knowledge, that's what goes under the rubric of reasoning and problem solving and thinking and deciding and choosing. We use this knowledge in our behavior, what's known in the trade as action, and then we communicate this knowledge to other people using the medium of language. So, major function of the mind is to engage in these cognitive operations to mediate adaptive behavior, to mediate the interactions between the individual and the world. Traditionally, this knowledge was construed in terms of associations of various kinds. First, there are associations among events, that is, associations between events that occur in the environment and between these events and the organism's response to them, but also associations between the organism's actions and their effects on the environment. So if the organism engages in some piece of behavior, what happens in the world outside? These are the kinds of associations that form the basis of traditional views of learning and thinking. It turns out that some of these associations, some of these stimulus-response associations are innate. They're pre-wired. They come as part of the organism's endowment. And we usually think about there being three general types of innate responses to stimulation. The first of these that we've discussed before are simple reflexes that involve individual muscles. The example we discussed before was the patellar reflex, where if you tap the patellar tendon, you get a knee-jerk response. That's an innate reflex. It's the way my nervous system, and yours too, is built. But there are lots of these in our repertoire. Another one that you'll see a lot of reference to is the eye blink reflex. When you go to your ophthalmologist or your optometrist for your annual eye exam, what he or she will often do is put you up against a little machine that presents a puff of air to your cornea. And there's a natural response to blink to that puff of air. That's an innate reflex. Nervous system's wired to do that. All reflexes are very simple stimulus response associations that are innate, and they involve the activity of individual muscles, single muscles. There's a single set of muscles in the eye that produces the eye blink reflex. There's a single set of muscles in the, actually it's the patellar tendon that produces the patellar reflex. So those are reflexes. We also have taxis, okay? The singular is taxis, and these are innate stimulus response patterns that involve the entire body, involve the entire skeletal musculature of the organism, so that the organism will basically move in response to some stimulus or another. We generally think of taxis as coming in two kinds. Positive taxis, where the organism moves toward some stimulus. Negative taxis, where the organism moves away from that stimulus. And there are also phototaxis, which are orientation responses to light. If you're out in your backyard after dark and you've got a candle going or a flashlight or whatever, moths will tend to move toward the light. They're displaying a positive phototaxis. They're moving toward a light stimulus. Some of the invertebrates, worms and things like that you find in your garden will engage in what's known as a negative geotaxis. They climb up things, okay? So they're orienting negatively towards the stimulus of gravity. If a worm or something will encounter a barrier, it'll move up, okay, and try to go over it. So taxis are also very simple stimulus-response connections, but in contrast to reflexes, they involve the entire skeletal musculature, or pretty much the entire skeletal musculature of the organism. And you see these taxis prominently in the behavior of invertebrate organisms, bugs of various kinds. And then finally, we have more complex innate stimulus-response connections that are known as instincts or fixed action patterns. These are innate patterns of behavior that are shaped by evolution to help the organism adapt to a particular environment. But unlike reflexes and taxis, they can be very, very complicated, okay? Very complicated patterns of stimulus and response. Here is a good example of food begging in herring gulls. This is work by Nico Tinbergen, won the Nobel Prize for this work. Very important in the history of psychology and behavior. Herring gull chicks, baby herring gulls, can't feed for themselves. They have to be fed by their parents. And the way parents do this, the way the adult gulls do this, is by regurgitating pre-digested food into the mouth of the chick. But they don't do this naturally. Okay? Well, they do it naturally, but they don't do it automatically. Instead, the adult herring gull feeds the herring gull chick only when the chick engages in what's known as a food begging response by pecking at a reddish or orange reddish spot on the lower mandible of the adult. So what happens is there's an adult, there's a chick. The chick will peck the lower mandible of the adult, and the adult will respond by delivering food into the mouth of the chick. The chick is responding to the presence of the spot on the mandible, and the adult is responding to the gull's chick. If the chick doesn't beg, it doesn't get fed. Okay? But, as Tinbergen found out, the chick doesn't beg unless there's an appropriate releasing stimulus in the environment. Here's an experiment that Tinbergen did in which he looked at the food begging behavior of chicks when they were presented with an adult with a usual orange-red spot on the lower mandible, lots of food begging behavior. Here, the adults had their spot painted black, okay? It's removable, right? But it was painted black. And the chicks still pecked a lot, still begged for food. When the bill was painted blue, they also begged for food quite a bit. But when the bill was painted white, remember that herring gull bills are kind of yellowy bills. You don't see it too much. There's less begging behavior. And when there's no spot, when the spot's been painted so that it blends right into the bill, there's very little begging behavior at all. So the releasing stimulus for food begging on the part of the chick turns out to be a contrasting spot on the lower mandible. And it doesn't really matter what color it is as long as there's a contrast. As long as there's dark against light, the animal will beg. But notice that this is now a very complicated sequence of behaviors. The chick has to beg. The adult has to have the right feature on its bill. If the adult doesn't have the right feature, the chick isn't going to beg. If the chick doesn't beg, then the chick isn't going to get fed. This is a characteristic feature of these instincts or fixed action patterns, that they usually involve very discriminative responses to stimulation. With the patellar tendon reflex, it doesn't matter what you hit my patellar tendon with. It can be a hammer like my doctor does. It could be a book. It could be an automobile. It could be anything you hit my patellar tendon with, and I'll respond in exactly the same way. But here, there's got to be that contrasting spot or nothing happens. And it's got to be responded to with a peck or nothing happens. So these innate behavioral responses to discriminative stimulation are shaped by evolution. And the point here is, the point I made last time too, that apparently evolution shapes more than body morphology. Evolution also can shape patterns of behavior, permitting various species to adapt to their environmental niche. And these instincts or fixed action patterns built in by evolution are fine. They allow organisms to live in their particular environmental niches, and that works fine so long as the environment doesn't change. But when the environment changes, this behavior that's been slowly shaped by evolution over eons of evolutionary time can come to be maladaptive. Very good example of this is a positive phototaxis in baby sea turtles. You've all seen this on nature programs and in television. Sea turtles, female sea turtles, come up onto the shore and dig a nest above the tide line, in which they deposit their eggs, and they go back out to sea and do whatever it is that adult sea turtles do. The baby sea turtles, when they hatch, what they end up doing, they crawl out of the nest and they run to the sea so that they can start swimming and doing all those other things that sea turtles are supposed to be doing. Now, it turns out that these baby sea turtles are not actually running toward the sea. What they're running toward is the light of the moon reflected on the water. It is a positive phototaxis. They're running toward a source of light. And that's fine, so long as there isn't any other source of light around. But in modern society, there are often lots of other sources of light on the beach. There might be automobiles on the beach. There might be an oil refinery nearby. There might be a hotel or a casino nearby. And what will happen is the sea turtles will run towards those lights as well. And if they happen to run toward the sea, everything works out hunky-dory for the sea turtle. But if the turtle ends up running toward the oil refinery or the casino or the all-terrain vehicle that just happens to have its lights on at that moment, things aren't going to go very well for the sea turtle. And so that creates a serious threat to the species. Okay, so what happens now is that this example illustrates some of the limitations of these innate responses to stimulation represented by fixed action patterns. First, in order for the instinctual behavior to occur, the stimulus must be physically present in the environment. For the sea turtles to run to the sea, the moon has to be out. There has to be an actual moon whose light is reflected on the water. For the herring gull chick to get food, there has to be a contrasting spot on the lower mandible of the adult. The second point is that because these behavioral responses, these instinctual behaviors, have been shaped by evolution, the organism isn't capable, by virtue of these innate response patterns, to respond to a new stimulus. Okay, either the stimulus is there or it isn't. You can't have conservation workers standing out by the sea and say, here turtle, come this way." They just can't respond to that at all. Put another way, these organisms, by virtue of individual organisms, can't acquire new responses to a stimulus. This response pattern has been built in by evolution. It's pre-wired, and they're not able to modify this in any way. And then finally, there is little opportunity for trial and error learning. Sea turtles have one shot at the ocean. If they make it, okay. Now, they might be eaten by a shark or something, but that's another matter. But if they don't make it, they don't have any mechanism for turning around and say, up, I must go the other way. You know, there's a fence here or something. They have no way of acquiring this new response, no opportunity for trial and error learning. The pattern has to work the first time, or the individual isn't going to make it. Yeah, there's a question here. Yes? Yeah, yes, can evolution change the response? Yes, evolution can change the response, but not for the individual. Okay, A, not for the individual, and B, not for the species either, except over extremely long periods of time. So you can imagine that, oh, maybe the light reflected from the moon is a different kind of light than the light that comes from the incandescent bulbs of an oil refinery or a hotel, okay? And you can imagine that over hugely long periods of time, that there's enough variation that the sea turtles that respond to moonlight will live, and sea turtles that respond to casino light won't live. But A, that assumes that there is such behavioral variability, okay? And B, that assumes that the species will last long enough for evolution to have to take its effect. We're killing species every day by virtue of environmental change. What's the big news besides the Iraq War? The polar bears, right? We're going to see the last polar bear in the wild in about 30 years if we're not careful, because their environment is changing, and there's not enough time left over for bears to discover a taste for bamboo shoots or whatever it is that they're going to have to live on. So these instinctual behaviors, these fixed action patterns, are very, very, very powerful, and they're very, very important for the adaptation of the species to its environment. But in addition to these instinctual behavior patterns built in by evolution, we need to have a mechanism for individual species members to modify their responses to stimulation. And that is what happens by virtue of learning. Traditionally, we'll revise this definition later, but traditionally we define learning as a relatively permanent change in behavior that occurs as a result of experience. A relatively permanent change in behavior that occurs as a result of experience. This definition is intended to eliminate changes in behavior that occur from the ingestion of drugs. Take some psychoactive drug or something that might change your behavior, but that's not learning, okay? Change in behavior that occurs as a result of injury. If you injure your leg and you can't run, that's not learning. It's a change in behavior, but it's not learning. And also changes in behavior that occur just by virtue of maturation. We don't put those in our definition of learning either. But again, there's a change in behavior that occurs as a result of experience. All organisms that have nervous system have at least some capacity to learn. Learning is especially important in vertebrate organisms, that is, organisms that have a spinal cord, and of course it's especially important in mammalian species and primate species like us. But whatever kind of species you are, if you've got a capacity to learn, learning permits the individual organism to acquire new behaviors under new circumstances. And it allows individual organisms to add behavioral responses to the environment, to whatever repertoire of stimulus response associations has been given them by evolution. Okay, so we're not going to actually talk about learning formally, but if there are any more questions about these instinctual behaviors, these fixed action patterns, I'd be happy to take them now. Anything at all? Yes. No, do the turtles come out in daytime? No, they don't. And the reason they don't is it's too hot. They're also responding to changes in ambient temperature. So it's got to be below a particular temperature, and then there's got to be some light out. And then if there is, then they start coming out of their nest, but there's got to be some kind of light. Unfortunately, there's almost always some kind of moonlight being reflected on the sea, okay? Every once in a while you might get a new moon that's really weak, or a lunar eclipse or something like that, but by and large, it's a pretty good mechanism, right? It's very, evolution is very smart in this way. It shaped this behavior so that the animals get to the sea. It's a very good cue to where the sea is, but it's just not so good anymore, okay, because of these kinds of changes. Anything else about these fixed action patterns? Yes? Taxis. Do humans have any positive or any kinds of taxis at all? We might. So probably don't really notice them, okay? Our behavior is governed by lots of other kinds of processes. Where you see them is in invertebrates, where they just, moths, let's be honest, okay? I'm not an anti-moth person, but moths don't do much else except fly toward light, right? And so you can kind of notice that. Cockroaches, okay? Cockroaches have what looks like a negative phototaxis. You walk into your friend's apartment or something like that, you turn on the light, cockroaches scurry. That's what they're built to do, and they pretty much don't do anything else except eat and run away from light. Yes?
So then what is it that attracts the adult sea turtles to go and
What leads the adult sea turtles to do what they do? And it's another instinct entirely, okay? When they're ready to drop their eggs, they come up, and it's interesting that the female sea turtle will come above the high tide line, because if you do your nest below the tide line, well, the eggs are going to get washed away. So that's another behavior that's been shaped by evolution. Generation after generation after generation of female sea turtles, the ones that laid their eggs above the high tide line, their progeny survived, and they had a tendency to lay their eggs above the high tide line as well. It's exactly the same thing. Could have used that example, except that the light example allows me to talk about environment change. And there are lots of these instincts. If you want a really wonderful read sometime, look at Nico Tinbergen's book, The Study of Instinct. It's a terrific book. It's real bathtub reading. Yes, quick.
can we learn from
Oh, can you learn from injury? Yes, you can learn from injury. Of course you can learn from injury. You stick your hand in an electrical socket. You don't do that twice, okay? But what we're talking about here is injury can produce changes in behavior, okay? Like if I stomp on your foot, you're going to limp around for a while. But the fact that you've now changed your behavior, that's not learning. That's just the fact that you're injured. We're looking at learning as a relatively permanent change in behavior that occurs as a result of experience. And you'll get a good idea about what I'm talking about when I talk about this first form of learning known as classical conditioning. Okay? So let's go right there. An early form of learning, one form of learning accidentally discovered by a Russian physiologist named Ivan Pavlov, who was studying the physiology of the digestive system in dogs. This is work for which Pavlov won the Nobel Prize in Physiology and Medicine. And his technique was quite simple. He'd confine the dog in this harness so it couldn't move around. He inserted a fistula, a little pipe, into the mouth of the dog to collect salivation, and then he would introduce into the mouth of the dog dry meat powder as a result, reflexive response to which the dog would salivate. Salivation is a reflexive response to the introduction of dry food into the mouth, and that's what Pavlov was studying. Initially, Pavlov's dog salivated only when the powder was actually placed in their mouth. But as the experiments went on, Pavlov noticed that his dogs would start salivating before the powder was presented. They'd start salivating just to the sight of the meat powder. Then they'd start salivating just to the sight of the experimenter. Eventually, they'd start salivating to the sound of the experimenter coming down the hall to start the experiment. Thus, what Pavlov observed was that this reflexive response to stimulation was also starting to occur in response to events that were in some way associated with the delivery of food. The sight of food, the sight of the experimenter, the sound of the experimenter, and so on. Pavlov recalled these psychic reflexes, by which he didn't mean psychics like, the psychics in the yellow pages, but he simply meant that this was a reflex that occurred to the idea of the stimulus. Remember how we defined reflexes and instincts before? That the stimulus has to be physically present in the environment? What Pavlov discovered was that sometimes the stimulus doesn't have to be physically present in the environment. The organism will respond simply to the idea of the stimulus, and it's the idea of the stimulus that will evoke a reflexive response. This is the basic procedure for what is now known as classical conditioning, as Pavlov and lots of other people have studied it. So what will happen here is that in the first phase of an elementary classical conditioning experiment, the experimenter will have these two stimuli. There'll be a bell, there'll be some food, and the experimenter will ring the bell and then ring the bell again and maybe put some food in the dog's mouth and ring the bell again and maybe ring the bell again, put some food in the dog's mouth. They're just kind of going off randomly. Then in phase 2 of the experiment, the situation changes so that the ringing of the bell is always followed immediately, within a couple seconds, by the presentation of food to the mouth of the animal, the dog. And you do that for a number of trials. And then in phase 3, you take the food away entirely and you just present the bell. And what Pavlov discovered was that on early trials here in phase 2, where the bell is followed by the food, not too much salivation occurred, but gradually the animal came to salivate to the ringing of the bell, so that in phase 3 on the test trial, you present the bell alone and the animal is salivating as if food had been presented in its mouth. This is the procedure of classical conditioning, where the ringing of a bell, a stimulus that did not originally elicit any kind of salivation, comes to elicit the salivary response, just like the meat powder would have itself. Okay, so this procedure now illustrates the basic vocabulary of classical conditioning, which consists of 4 terms. First, we have the unconditioned stimulus. The unconditioned stimulus is a stimulus that reliably evokes some reflex on the part of the organism. Unconditioned stimulus, an environmental event, a stimulus that reliably evokes a reflex on the part of the organism. Presenting dry meat powder in the mouth of a dog evokes salivation as a reflex. Tapping my patellar tendon reliably evokes a knee-jerk reflex. Putting a puff of air on the cornea of my eye reliably evokes an eye blink reflex. So that's the unconditioned stimulus. The unconditioned response is the reflex that's reliably evoked by the unconditioned stimulus. The salivation, the knee-jerk response, the eye blink. Okay, so the unconditioned response is the reflex itself. The unconditioned stimulus is the event, the stimulus event, that elicits that reflex. Then we have the conditioned stimulus, which does not, in and of itself, elicit any reflex on the part of the organism. If you ring a bell, I don't salivate ordinarily. My knee doesn't jerk ordinarily. My eye doesn't blink ordinarily. It just doesn't have any effect on my behavior. But if you repeatedly pair the conditioned stimulus with the unconditioned stimulus, bell, food, bell, food, bell, food. Then what will happen is that the conditioned stimulus, the bell, will come to evoke a conditioned response, like salivation, that in some respects resembles the unconditioned response. So what happens now is that the conditioned response is the response that's evoked by the conditioned stimulus after many pairings with the unconditioned stimulus, and it's a response, the conditioned response usually resembles the unconditioned response. Doesn't have to, but it usually does. So that's the basic vocabulary of classical conditioning, and we can use this basic vocabulary now to work our way through some of the major phenomena. The first phenomenon of classical conditioning we want to talk about is acquisition. Acquisition is the process by which a conditioned stimulus acquires the power to evoke a conditioned response. The process by which a conditioned stimulus acquires the power to evoke a conditioned response. And this happens by virtue of what's known as reinforcement. Reinforcement, which in classical conditioning simply means the pairing of a conditioned stimulus with an unconditioned stimulus. Pairing of bell food, bell food, bell food, bell food, over and over again, the bell will come to elicit salivary, some kind of salivary response. In general, we measure the acquisition of a conditioned response in terms of its strength, and there are two big measures of strength here. One is the magnitude of the conditioned response. How many drops of saliva does the animal give in response to the bell? On initial trials, not much. On later trials, lots and lots. So the conditioned response is growing in strength. Or we can simply measure the strength of the conditioned response in terms of the probability that the animal will give up the conditioned response. That is, the probability that the dog will salivate at all. Okay? So that's the acquisition phase, and it kind of goes like this. On the first trial of acquisition, we might present a conditioned stimulus, a bell, that rings for a while, and then a little bit after the onset of the bell, we present food into the mouth of the organism. And what you can see here, this is the very first trial of acquisition. The animal doesn't respond when the bell comes on, but does begin to respond as soon as the food is presented. This is the reflexive response to salivation on trial 1. There's now, as yet, no response to the bell. Then a couple more trials, 10 more trials maybe. The conditioned stimulus comes on a little bit later, second or two later. The food is presented into the mouth of the dog. But notice that now the animal is beginning to salivate after the bell starts ringing, but before the food is presented. This is the first appearance of a conditioned response, a response to the conditioned stimulus, not to the unconditioned stimulus. And then carry this out for some more trials, maybe 20 trials. Now you can see the animal is emitting the conditioned response immediately after the onset of the conditioned stimulus, long in these terms, long before the food has been given. The acquisition of a conditioned response looks pretty much like that. On the first trial, nothing happens. As trials go on, pairing of the conditioned stimulus and the unconditioned stimulus, bell food, bell food, bell food, then the animal starts responding to the bell as if it were food, responding to the bell because it's being associated with food. Here is a typical pattern for the acquisition of a conditioned response. Here we have number of trials. Here we plotted the probability of eliciting the conditioned response, salivation or whatever. On early trials, not much conditioned response. Gradually, through reinforcement, the conditioned stimulus acquires a lot of strength to elicit the conditioned response. This is acquisition by virtue of the pairing of the conditioned stimulus, the bell, with the unconditioned stimulus, the response. Okay, so that's what the acquisition phase looks like. In acquisition, the conditioned stimulus acquires the power to evoke a conditioned response. In extinction, the conditioned stimulus loses the power to evoke a conditioned response, and it does so by virtue of the lack of reinforcement. Now what we do is we disconnect the link between the CS and the US, the link between the bell and the food, so that now the bell's presented, but the food's not presented anymore. Bell, nothing. Bell, nothing. Bell, nothing. And what happens is the conditioned response eventually loses its strength. You have a question over here? Oh, okay. All right. So let's see how that works. Again, on extinction, trial 1, first time the bell is presented in the absence of food. The animal doesn't know the situation's changed, right? So gives a strong conditioned response. After 10 extinction trials, the conditioned response has been weakened. Again, we're presenting the bell but not the food. Conditioned response has been weakened. And finally, after some more extinction trials, the conditioned response drops out entirely. Here's the pattern, typical pattern by which extinction occurs, and you see it's pretty much the mirror image of acquisition. On early trials, the conditioned response is very strong, and then it gradually weakens, loses most of its strength early in extinction, and then as the extinction trials are carried on, it drops back to zero, or at least back to baseline. Acquisition, by virtue of reinforcement, the conditioned stimulus acquires the power to elicit a conditioned response. Extinction, by virtue of the lack of reinforcement, the conditioned stimulus loses that same kind of power. But it loses it in a funny way. If an animal acquires a conditioned response through reinforcement in the acquisition phase, and then that conditioned response disappears during extinction, if you take the animal out of the test apparatus, put it in its home cage for a while, and then bring it back into the test apparatus and just present it with a conditioned stimulus, just ring the bell, what you're going to see is some spontaneous recovery of the conditioned response. So if you give the animal some rest after extinction and then retest it with a conditioned stimulus alone, you will see some degree of conditioned response being given. So that's what we mean by spontaneous recovery. There haven't been any new acquisition trials. There have been no new trials in which CS and US have been paired with each other. It's just that the conditioned response spontaneously recovers after a period of rest. Okay, so here we go. Here's the acquisition phase. The conditioned response growing in strength. Here's the extinction phase. The conditioned response loses strength. Now we have an interval of rest. We test the conditioned response again, and we see that there's some strength there, okay? And now if we carry out further extinction trials, then the conditioned response will again go back to baseline. This is what's known as spontaneous recovery. And spontaneous recovery is itself subject to extinction. You can just keep carrying out these extinction trials. Okay? The next phenomenon that we look at is the reacquisition of the conditioned response. After you've extinguished a conditioned response by taking away the reinforcement, then if you start reinforcing the conditioned stimulus again by pairing it with the unconditioned stimulus, bell food, bell food, bell food, then what will happen is that the animal will start showing the conditioned response all over again. Okay, the conditioned response will grow in strength. But what's interesting about this is that on reacquisition trials, when the CS is once again paired with the US, the animal will condition up again, but will condition faster than it did on the initial trials. Even though the response was extinguished, the animal will relearn the conditioned response faster on subsequent trials than it did on the initial trial. This is a phenomenon known as savings in relearning. Spontaneous recovery and savings and relearning reveal two important, features that reveal something very important about extinction. And that is that the conditioned response isn't really lost during extinction. It's not forgotten. It's not as if it never was there, okay? It's there. The animal still has the capacity to make the association between CS and US. Otherwise, it wouldn't relearn it faster the second time around. Had a question back here? If you do this over and over and over again, the animal doesn't get confused. That's a very good question. You think the animal will say, hey, what's going on here, right? But that's, for reasons that we'll talk about next Wednesday, okay, that's not exactly what happens. What happens is, when you repeat the cycle, the animals catch on more and more quickly. So that, let's go back here for a second. So that if you repeat the acquisition phase, the animal shows savings in relearning, okay? It says, oh, okay, bell's followed by food now, so I'm going to start salivating. Then when you repeat the extinction phase, the animal extinguishes more clearly. It shows savings in extinction, if you will. The animal says, okay, bell isn't associated with food anymore, so I won't salivate. I mean, that's not what the animal's actually saying, but that we're anthropomorphizing here for purposes of the discussion. And then when you turn the connection back on, the animal will catch on to that immediately, okay? So you get lots of savings in relearning, and you get lots of savings in acquisition. The animal will adjust its response very, very finely to what's happening around. So, okay, bell and food are associated now, so I'm going to salivate. All right, bell and food aren't associated anymore, so I won't salivate. And it basically works like that. There are ways to confuse animals with procedures like this, but we're not going to talk about those today. Quick question, yes? Does it depend on how old the animal is? It doesn't really depend, okay? Even baby animals can show classical conditioning. Infant humans can show classical conditioning. I suppose I've had a teacher who did classical conditioning experiments with college students. And under those circumstances, college students can just think too much about the situation. They usually screw up these experiments. But no, age doesn't really matter. It doesn't really matter. As long as the organism is capable of sensing the stimuli and performing the response, okay, really doesn't matter. This is a very, very, very elementary form of learning, and it's widely available, okay? So what else do we have to say here? Okay, so we've done acquisition, okay? Here's savings and relearning. You've acquired a response, you've extinguished the response, there's been some rest, little spontaneous recovery. Now you put the animal on reinforcement schedule again. The animal will show savings and relearning. It will reacquire the response faster than it acquired it the first time. Okay, so that's the point here, that conditioned responses aren't lost during extinction because they come back, okay, and they come back faster. Okay, here is another phenomenon. I can finish this before our time. The generalization of a conditioned response. Once a conditioned response has been established, then you can transfer, if you will, that conditioned response to other stimuli. What will happen is, once a conditioned response is established, the animal will also give the conditioned response to other stimuli in the environment, provided that they are similar to the stimulus to which the animal was originally conditioned. This is what's known as the generalization gradient. Here is an illustration of it. We imagine that we conditioned an animal to a tone of about 650 cycles per second frequency, and then tested the animal's response to lower tones and to higher frequency tones. What we'll find is that the animal responds best to the tone to which it was initially conditioned. But it will also respond pretty well to tones that are close to the original tone in frequency. And there's a progressive drop-off in response as the test tones become more and more dissimilar. So the generalization gradient is a gradient of similarity between the test stimulus and the original conditioned stimulus. And the idea behind generalization is that the more the test stimulus resembles the original CS, the more conditioned response you'll get. The more dissimilar the test stimulus is to the original CS, the less of a conditioned response you'll get. Finally, we have a phenomenon known as discrimination, which accounts for essentially a check on generalization. Here, what happens is we take one conditioned stimulus, say a bell of a particular frequency, and we reinforce that with food. High bell, food. High bell, food. And another bell with another frequency, low bell, okay? And we don't reinforce that with food. High bell, food. Low bell, no food. What will happen is the animal will come to make a discriminative response so that it gives the conditioned response only to the conditioned stimulus which has been reinforced, and it won't give the conditioned response to the conditioned stimulus that's not reinforced. Here is a schematic of what discrimination learning looks like. Here we condition the animal for a while, okay? The 500 cycle per second bell is paired with food. The 250 cycle per second bell is not paired with food. For a short while, the animal just responds to bells, right? But pretty soon it begins to make the discrimination. The response to the reinforced stimulus, the reinforced CS, continues to grow in strength. The response to the unreinforced CS, that strength drops out. This is essentially extinction, right? This is essentially acquisition. This is essentially extinction. So what happens now is that by virtue of these basic processes, okay, acquisition, generalization, discrimination, stimuli come to evoke and inhibit conditioned responses, even though they themselves have not necessarily been associated with the conditioned stimulus. Okay, so that's what's going on in classical conditioning. By means of classical conditioning processes in general, what happens is that reflexive behaviors come under the control of environmental events. Classical conditioning phenomena are ubiquitous in nature. Basically, any organism that's got a nervous system will show at least some of the phenomena of classical conditioning. They may not show them all, but they'll show at least some. In each of these cases, we're extending control over reflexes to other environmental events. I start giving the patellar reflex to the sound of a bell instead of just the blow of a hammer. Pavlov believed that all forms of learning were basically variants on classical conditioning. We now know that that is too extreme, but we do understand now that to a very large extent, the laws of classical conditioning are the laws of our emotional lives. By virtue of processes like classical conditioning, we acquire our fears, our aversions, our joys, our preferences, the things that make us happy, the things that make us sad, the things that make us afraid. Some of those things make us that way innately, but most of them make us that way because we have learned to respond that way to these events, and we've learned to respond that way to these events by virtue of a process very similar to what Pavlov studied as classical conditioning. Thank you very much. Have a good weekend. I'll see you Monday.